Hi friends, this is a dummy recording and I'm recording my presentation which I have done in Suntech Day 2010 I believe, and we had a talk about the garbage first algorithm, and luckily we have given a default server side algorithm in JDK9, so that's a great news. So please pardon me because it has all the Sun template. I'm Vaibhav Chaudhary, and we will see a little bit of G1. Before seeing into the G1, we'll see a bit basics of GC. So yeah, that's our agenda. We are going to see the basics of garbage collector, and then we'll go into the G1, and we'll talk about the garbage first attribute and the garbage first operations. What are the recent changes? And these recent changes I'm talking about 2010. And what are our final thoughts on G1? All right, so this goes a very popular picture of Java heap space. Let me explain you a little bit in detail here. So the Eden generation is actually the new generation, and you have tenure, that is the old generation. And there are two survivor space in the Java heap, that is S1 and S2. I have just wrote it both as S. And then we have permanent generation. Now actually after JDK 8 we don't have permanent generation, so we have something like metaspace in that place. Okay, so the minor GC happens in young generation. That happens quite frequently than the major GC, and the major GC happens in old generation as well. Okay, and these are some of the flags like XMX and XMX which we set. So XMN, if you will talk about it, is the total heap space provided in the young generation. XMX, if we're talking, it is the total JVM heap. So XMX is actually a symbolic representation of out of memory. So if your application is going out of memory, you just look into your XMX. Let's not go more detail about it. So before going into the G1, we'll talk a bit about the weak generational hypothesis. This is a very important thing, and mostly, not mostly, all the GC that is in the hotspot follow this weak generational hypothesis. You can see plenty of papers written on the web, but in a nutshell, it has two basic observations. It says the most of the objects die young. Okay, I believe it says 80 to 20 ratio. So 80% of the object die young, and very few of the objects survive to the young and it go to the old generation. Like if you are considering your swing frames and something like frames and the sliders, those objects actually live for a very longer time. And the second observation is that you have very few old to young references. Okay, so on this basis, we can smartly divide our Java heap space into two areas. One is called young generation and one is called old generation. That's exactly the one we have shown here. The green color is actually the young generation, and the blue one is the old generation. So with this division, what we will do, we will focus mostly our GC to work in the younger generation, and it will give a very good payoff, because most of the object die young, so we can get a lot of space emptied in the younger generation. Okay, so yeah, it will give you a lower GC overhead, and it will most of the pauses are short actually. Yes, so why generational hypothesis? So most Java application actually confirms according to the weak generational hypothesis. Weak generational hypothesis is actually very tough to beat, and it's in the most of the cases. Rather than, I will say, in all the cases, it is performance-wise it's tough to beat. And all the GCs in the hotspot JVM follow the weak generational hypothesis. That's why we say all the GCs are actually the generational GCs. Yes, so these are some of the definitions which are very important for us to understand. And we will keep using these terms very frequently in our later slides. What do you mean by mark? Mark is finding an accessible object from the root that that is called mark. Okay, so it's like marking. Actually, it's like finding and marking. You just raise a flag on it. Then we have something called sweep. Sweep is reclaiming the unmarked object. Then copy is more like moving the live objects from one part to another part. You must have seen the 2 survivor space, and we use survivor space very heavily for doing the copy. And then compaction. Many garbage collector algorithms do compaction, and many don't do compaction. So compaction is moving all the live objects into a contiguous memory allocation, because when the GC will scan, through your heap space, and it will do marking and sweeping, there will be a lot of fragmentations that will raise in your Java heap space. So compaction is required or not required. This is we will discuss this into the coming slides. Again, this is very too important term to understand how the GC works. So parallelism and concurrency are talked interchangeably, but these two terms have completely different meaning. Parallelism means all the application thread can run in parallel, and if the JC thread is running, all the GC thread can run in parallel, but it will stop all the applications thread. Okay, so what you are seeing in the first part and what you are seeing in the second part is actually parallelism. Whereas the concurrency says that GC thread can simultaneously run with application threads, like what you are seeing in third or what you are seeing in the fifth. Okay, so for our further slides, this is a very good reference, and we should remember this. These are some of the GC algorithms that we generally use, and let's have a look at when to use, what to use when. Okay, so we have a serial GC. Serial GC is simply copying young, and it's stop the world, and you can directly use -XX use serial GC. Then we have parallel GC algorithm, which is again stop the world, but it is a multi-threaded GC algorithm. And then we reach to mark CMS, that is compact mark and sweep. So compact mark and sweep is again stop the world, and you can just use conc mark and sweep GC. In the previous slides, I have not explained you what is actually stop the world. So stop the world is nothing. It says that when GC is start, it has to stop the application, and that is what precisely we mean by stop the world.